Swayam Prabha. Digital India. Educated India.
In the last few classes we were speaking about combustion instability involving dumb combustors and so on. So what we saw was the predominant features in the dumb combustor, the kind of fluid mechanics that happens, the kind of heat release rate that happens, and how the fluid mechanics affects the heat release rate and so on. Nevertheless, we did not learn any quick calculation procedure because there is no real simple quick calculation procedure. What we would need is to experimentally study it, we will have to use the experimental devices like you have to use measurement devices like pressure transducers for the acoustic pressure, like piezoelectric transducers or microphone, and to see the flow we can do optical flow diagnostics. To see the velocity field we can either use particle image velocimetry, which will give a whole field view, or laser Doppler velocimetry to get the spectrum and so on, and we can do to see the combustion we can use planar laser induced fluorescence or even chemiluminescence and so on and so forth. To be able to calculate we have to make a model, and it's the phenomenon is so complicated that you cannot make a simple it's a very simple model. We have to actually solve the partial differential equation of the flow and combustion, so which would necessarily mean we have to use CFD, computational fluid dynamics, and in the end we have to get the heat release rate, which you can directly, then there are two possibilities. So we can actually couple it with the time domain solution, and we can march step by step both in the acoustics as well as in the combustion, step by step in a very closely coupled manner. So that would provide you a time domain solution, right? And what is the other alternative? Either you can solve in time domain or in frequency domain, and for that we would in the linear analysis what we would do is we would distill this combustion response into a transfer function and feed it into the analysis in the form of an n-tau model or something, and if you are in a time domain you do not have to do it, you just have to march directly, and you can do a linear or a non-linear simulations, and so which we have studied actually. So we have learned quite a bit, that is how to analyze the system in time domain as well as in frequency domain. The important catch here is how to get the heat release response. Once you do that we know how to solve the problem, and I told you that how to catch the heat release response is not a very trivial problem, it has to be solved keeping all the physics in that. So if you are looking at a Bunsen burner kind of flame, we wrote the equations and we learned how to do it. We did it for did you do it for any other one? For a lean premix pre-vaporized combustor we made a model which was driven by equivalence ratio fluctuations, but then so in the same manner if we have a model then we can do the analysis, and then once we have the analysis we can find the eigenvalues, we can find the growth rates, we can or the decay rates, we can find the frequency of oscillations, we can find we can perform the non-normal stability analysis and look at growth factor and so on. We can draw the bifurcation diagrams using continuation methods or direct time marching. So we have actually learned quite a bit in the course. The only thing that we have not learned a general prescription is to get a simple relation for heat release just like that for any combustor. So that is elusive, and that is elusive because it is quite a combustion is a inherently difficult and intricate and complex phenomena, and so we have to calculate it properly, understanding all the physics, and if therefore you have to do the experiments because you may have a model and we have to ensure that the model captures all the physical phenomena that you see in the experiment. So this is by definition a very complex process, therefore the calculation will also be complex and you have to be very careful, and we cannot wish this away. So I hope you have got this message. We also briefly looked at some aspects of passive control very briefly, and so the several other combustors were stabilized combustors, solid rockets, liquid rockets. Solid rockets itself will have composite propellant or double base propellants. So each of them would have a different analysis because in each case the flame is behaving differently. In some case the flame will respond to the pressure oscillations if there is a pressure coupled response in solid rocket motor, as the pressure goes up and down the flame would behave differently, whereas in some other combustor the flame may not respond to the the flame may not respond to the velocity fluctuations at all. Flame may be responding to only pressure fluctuations, or some other set of combustors flame may respond only to the velocity fluctuations and not to the pressure fluctuations, or in some complicated situations like rockets sometimes flame responds both to the velocity fluctuations and the pressure fluctuations, and also we have this time delay and so on. So this is the case, and this is what we have learned. Now the only thing that, just to re-emphasize, is which we have left loose is a general strategy to calculate heat release rate, but if you are confident to do combustion CFD, unsteady combustion CFD, which I trust you can learn it from some other classes or on your own, and then we have the framework to study the linear and nonlinear analysis thermoacoustic instabilities. So in this context, do you have any general questions? Too early in the morning for questions. Okay, so we did speak about passive control of instabilities. We will take a brief look, very brief, equally brief look at active control instabilities. This is not going in any depth, or I am not going to go to a depth like we did the n tau analysis with eigenvalues and the frequency domain on the time domain. So if after my lecture you would not learn how to analyze, how to design a controller or anything, but I will just give a very brief introduction to that. That is all I can hope for, because anything more would need a very large number of lectures and in-depth knowledge of control, which I am myself not working in active control. So to summarize, combustion often arises due to a coupling between the unsteady heat release and the acoustic combustion oscillations occur because of the coupling between unsteady heat release and the acoustic waves. So I mean the key is to remove the coupling, or if sound comes, take it out. That's the idea of control. And in this context I have two references for active control of combustion instability. That's what we will do today. So Ann Dowling and Amy Morgan's feedback control of combustion oscillations in this journal, Annual Review of Fluid Mechanics, volume 37, page 151 to 182. Annual Review of Fluid Mechanics is a impressive journal in which every year the editorial board looks at what are the developments that are there, and if some subject has come to some level of understanding or closure, and then they are starting off in some other directions, they will invite the best person in the subject to come and write an article, and you can't just go and send them an article. And so that is Annual Review of Fluid Mechanics. So it's a very prestigious thing to get an invitation to write there. So this is a relatively new article in 2005, and then this one we have looked earlier when we started off the frequency domain analysis by Keith McManus, Thierry Poinsot and Sebastian Candle, a review of active control of combustion instabilities, Progress in Energy and Combustion Science, volume 19, 1 to 29. And so this one, the first one, has more recent stuff. This is older stuff, much older stuff, and a lot of things happened in between, and so it's worth reading both, because then you get the idea of how the subject evolved. So unsteady combustion is an efficient source of acoustic oscillation actually, and combustors tend to be highly resonant systems. If combustor didn't resonate, if you are never having a confinement, then if you are always burning everything outside, then we wouldn't have combustion instability, because the waves are going, they are not coming back to create any problems. So therefore when unsteady heat release rate generates acoustic waves, they reflect off the boundaries of the combustor and produce flow unsteadiness near the flame, and that's the key thing, flow unsteadiness and heat release unsteadiness. So this may cause more unsteady heat release, for example through we saw many mechanisms, local changes in fuel air ratio, through hydrodynamic instabilities, through flame area modulations, or through change in mixing patterns. So many ways you can have unsteady heat release coming up, and we saw a bunch of mechanisms. To eliminate combustion oscillations, the coupling between the acoustic waves and the unsteady heat release must be disrupted, then you do not get oscillations, and this is the key stuff. So people did passive control methods. We saw that that included modifying fuel injection systems or the combustion geometry, or removing energy from the sound waves using acoustic dampers, perforated plates, baffles, liners, Helmholtz resonator, quarter wave tube. So in this we are not really not having, see in the active control we have the instability and then we do something simultaneously to keep it balanced, but in passive control, okay, we try to do something passively, that means we do one thing and leave it there and then let us see what happens. So we are not dynamically pulsing the fuel injection or keeping a loudspeaker on. Passive means we do something and then we see what happens, okay, that is the idea. So the problems with passive approach is that they tend to be effective only over a limited range of operating conditions. They one size won't fit all, and they are very ineffective at low frequencies for some reason, because low frequencies it is quite difficult to damp the oscillations, and changes in design are usually costly and time consuming. When you go to these meetings where they are trying to solve combustion instability, they will say that somehow stop it but do not change anything, and this is kind of I do not know, you would have to be a spiritual guru or something to magically pump spiritual energy and stop it, or something like that, but that is what they say. I am telling from my experience. So the other possibility is active feedback control or active control of combustion instability. So here we, as opposed to passive, we actively meddle with things and actively try to disrupt the coupling. So we have an actuator which modifies some system parameter in response to a measured signal. So this is the crux of the active control. Again, you can have many actuators, but I just write it symbolically. So the key thing is measured signal. So we are kind of live, we are measuring what is happening, and then we have actuator, and actuator tries to modify some system parameters, and it is in response to the measured signal. So that is the that is what you mean by active control. The aim is to design the controller and such that the unsteady heat release and acoustic waves interact differently. There is some way of interaction and then you want it to interact some other way, okay. So the controller means the relationship between the measured signal and the signal used to drive the actuator. So that is actually the meaning of controller. So controller would mean it is a relationship, that is what it is, between the measured signal and the signal which is used to drive the actuator. So that is what meaning of controller. So the aim is to design a controller such that the unsteady heat release and acoustic waves interact differently as in we want to make the acoustic oscillations die down. We can also have the controller such that you set up oscillations. For example, if you want to set up the first mode or the second mode, and you can program a controller that it will set up the natural frequency. You do not need a frequency generator to set it up if you have active controller, but generally we want the oscillations to die down or decay down, so that we do not have combustion instability. So that is the idea. Is this clear, this basic concept? So so what I am going to discuss is to I think to learn about controller you can take classes learn about feedback control, you can take classes in chemical engineering where they have many classes in control systems, also as well as in electrical engineering where also they have classes in control theory. Here I will deal with some specific thermoacoustic issues which will perhaps kindle your interest. So implementing feedback control around practical controller system requires one careful choice of sensor and actuator. Assuming that we know how to deal with a controller, attending a course in electrical engineering or chemical engineering, and you get everything into your head, and let's say we can design the controller and we have the equations, or we have we either have a model based controller or we have a controller which is based on system identifications where we do not worry about model, let the system run, identify what is going on, and then we have any one of these things. So then how would you deal with it, that is the system. So we have to have a careful choice of sensors and actuators which will work for our thermoacoustic instability. I mean actuator which works for something else may not really work here. So sensor must provide a measurement of a dynamic quantity relating to combustion oscillations, because our quantity is fluctuating quantity by definition, as opposed to some other processes where you may have an input and output and you want to control the rate of output depending on what is the input and you want to change it. So that those are like not dynamic processes, but they are kind of I don't know, non-dynamic processes. But here we have oscillatory phenomena by definition, so we have to be able to capture the oscillatory phenomena. If you have any questions you can ask me. Sensors must provide measurement of a dynamic quantity related to thermoacoustic oscillations. So although this is a kind of straightforward task for the unstable system, it is more difficult for low amplitude control low amplitude oscillations, because if the system has become unstable and then bang bang oscillations happen at very large amplitude, then everything will work. But the idea is we want to use linear controller which will work at small amplitudes, and because if you let the amplitude go very large, then the oscillations are in nonlinear regime and they are very loud and maybe the system is already destroyed and so on. So we want to have them work at low amplitudes, and at low amplitudes if you have your controller to work, your sensor has to work at low amplitude. But anytime you want to measure something, the smaller the signal strength, the more difficult the measurements will be, because in thermoacoustic instabilities there will be, in addition to this instability signal, there is always this background turbulent flow, and this makes things quite difficult. So the possible candidates are microphones and piezoelectric transducers. Usually microphones would mean condenser microphones, or we have piezoelectric transducer which can measure the dynamic pressure. You can also have piezoresistive transducers which measure the fluctuating plus the steady part, but they are more expensive to buy. So the advantage of using acoustic transducers or sensors like microphones and piezoelectric transducers is sound always propagates. So if something is happening here, you do not have to go here, you can stand there and listen. I am standing here, and thanks to acoustics you can sit there and do not have to come near me. If the mode of propagation of this information was not acoustic but hydrodynamic or something, then you would have to come very close to me, thankfully not. So we can measure acoustics standing from quite far distances, and combustors are typically a few meters long at the most, so definitely sound will propagate that much, there is no problem with that. Now so it is not that we can, I mean you may not want to come close to me, but there is no particular difficulty in locating the transducer anywhere. For example, if the sound is produced at the combustion zone, you can place the transducer there, it is not having difficult to access. Maybe you can water cool, and we can make sure that the structural integrity is not spoiled, but the transducers may get spoiled if they are very close to flame or something. So there is an option to keep them away and you can still measure it, and typically microphones have large bandwidth and they are reasonably robust. Particularly microphones may break at large amplitude, but piezoelectric transducers are, and microphone if you drop it will surely get spoiled. Piezoelectric transducers, they are much more robust. So just to tell you a story, I used to have microphones, that is what I used as a PhD student. I was very careful, handled them like babies because they are very expensive, each cost like 2 lakh rupees and so on, and I bought many of them, and and had and I had many B.Tech students working with me, and they were dropping it and destroying it, and many were dropped. So after that I decided to switch to piezoelectric transducers. So I dropped microphones as well as the B.Tech student because this was very expensive. So even if and you are not careful, so this is more robust, but I think you can use, there are microphones which will take 180 dB or 165 dB without breaking. So if you are careful you can use a microphone, but it is very expensive. We do not need microphones because microphones have very high bandwidth. This condenser microphones, they can measure sometimes 20 kilohertz or even 80 kilohertz and so on. The aeroacoustic people use that because many times they want to scale the spectrum, and therefore they have to have maybe they measure a small jet which has very high frequency and then scale up to large jet. So the spectrum, their frequencies may not be so much, but when you scale down you may have large frequencies. We do not have any such problems because we get frequencies of the order of I mean 50, 100 to several hundreds or 1000 hertz. So microphones or piezoelectric transducers both will work very well. The piezo transducers are like roughly half the price of the microphone, 1/3 the price of the microphone. So although I said that the microphone can be located anywhere, sound will travel, the location itself is quite important because we may have pressure nodes, that is pressure minima, and we have to ensure that we do not locate the microphone at a pressure minima, or even if you have, it may be possible that a good location for one thing may be a bad location for some other thing. Generally it is like that. If you want best of something, for sure he will have, or that thing will have the worst of some other thing. Okay, I mean life is like that, and if you don't want and if you don't want to lose out on so much, then you won't lose out on the other thing also. You can be in the middle, little bit of this, little bit of that, or you want to have best of something, worst of that, or you want to have the best of the other thing and worst of that. So it's the same thing. If you want the best microphone signal, you have to be at a pressure maxima, but generally that location will be minima for another mode. So then you have to cover your bases by putting at least more than one, so that if this minima comes, the other maxima is captured, or at least some reasonable measurement. So some kind of commonsensical trade off would be necessary, so so that you don't miss out on the signal by having them located on the pressure nodes or the pressure minima. And if you are having the azimuthal modes, then you need many microphones so that you can get the phase right, and there you have to have many microphones, only then you will know which mode it is. The most common alternative to measure the heat for measurement of the dynamic quantities other than microphone, what else is oscillating? Sorry, other than the pressure signal, velocity is oscillating. So how do you measure velocity? Hot wire. That's very expensive measurement compared to microphone, because hot wire system will cost like about 30 lakhs or 25 lakhs, even a cheap one, as opposed to 2 lakh for a microphone or piezoelectric transducer, which is 1 lakh. So what else? Other velocity measurement, laser Doppler. So that is 1 crore here we are talking about. So again that is going worse. Again same with particle image velocimetry, that is of the order of 1 crore, plus you have to have elaborate processing. So I think measuring velocity is in general a bad idea. If you just want to measure velocity and see, if you put a hot wire in a hot zone, you wouldn't measure anything, you have to have a cold, and combustion is by definition hot. So some people use in the laboratories hot wire in the cold zone just to measure the fluctuating velocity in the base of the flame where it is cold or something like that. So that is the best you can do. So in general we will not try to measure velocity. So pressure yes, velocity no. Of course there are people who have lots of money and lots of equipment, and just because they have this and you have to may use this, but in general I wouldn't recommend this. And what other thing can we measure very peacefully, very easily? Sorry, I see your lips moving, but I don't hear anything. Temperature fluctuation. And how easy is it? See, lips moving, but I don't hear anything. So no acoustics is coming out. Don't. Thermocouple, yes, that is a good point. Will it calculate, will it capture these fluctuations? There are for low frequency oscillations there are fast acting like fine micron size thermocouples, but the problem is it's the frequency of response of the micro thermocouples is varying with frequency. So the response of the thermocouple. So you have to elaborate calibrating mechanisms, and there are transducers which can measure temperature fluctuations, but they don't work that easily and that well, and you have to have large enough fluctuations in temperature. So, and there may be cases where temperature may not be fluctuating, but mass flow may be fluctuating, and therefore this may not work out. So temperature fluctuations, yes, we can. But in general not that easy with thermocouple, and with opticals, and Viksha said that you can do it with optics imaging. So how expensive? See, imaging can be done with your cell phone camera, and then it's wonderful. So is it possible to do that?
It's possible, it's being done. Imaging has been done.
So temperature, the typical, the most successful technique is 2-line planar laser induced fluorescence, which will cost probably 2 crore or something like that. So I think I will rule that out. So what else is left over? Heat release rate, perfect. So Q prime of, and how can we measure this? So we can do that with PLIF, but again that is expensive, but that is possible. What else?
We can measure if the
PLIF is planar laser induced fluorescence.
If the fuel flow is oscillating, we can measure that and find.
How can we measure heat release rate?
Directly.
We actually spoke about it in last class briefly. Ganesh, how are you doing it in your experiment?
Actually, I am going into a pressure transfer.
Okay, how are your friends doing it?
This means
You have seen them use some camera, but no lasers, right?
yeah.
So what are they measuring?
They are measuring radicals.
Radicals, yeah, so chemiluminescence, perfect, thank you. So people measure OH or CH, CC, these are the radicals that are, sometimes you put OH star, CH star to show that it's a radical. These are the radicals that are there in the flame zone. So if you just take a video camera and look at a flame, you will see a flame, but that is not just the heat release zone, but you will see some other things also. What else will you see? See, if you look at a Bunsen burner flame, you will see a flame like this, but maybe you have a very fine place where all the combustion happens, but the entire thing will glow like that. Yeah, so radiation from the gases or black body radiation or whatever. So we don't want that. That's why we need this chemiluminescence, because we want to look at the place where the reactions predominantly happen. So in the places where reactions predominantly happen, there will be activated species which are occurring only in those places like OH, CH and CC. So we look for that. How do you look for that, and how do you not see? Yeah, filter. I am reminded of Swami Vivekananda's quote, if you wear blue glasses you will see the world as blue. So if you wear blue glasses you will see CH, so world as CH, and if you wear UV, so this is like I think 308 nanometer for UV, CH is 428 or 427, I think CC is 500 something, I don't remember. How much? 510. 510 nanometer. So you can use narrow band pass filters which will let only this light go, so that we see only that, and a lot of things are coming, we just focus on what we want. And this for a perfectly premixed flame, OH is a CS, they are direct markers of heat release rate. Sometimes this may be influenced by a lot of other things. For example, if there are equivalence ratio fluctuations, this will depend on that also, and so on. So it will not be a direct indicator, it may be like have to be corrected for that and so on, but nevertheless if there are heat release fluctuations this will also fluctuate, only dependence may not be linear and so on, but there will be fluctuations. Now the problem is you can't stand away and measure these things because this you have to see the flame zone, that is the thing. About the other things in the signal we can filter them out by putting in narrow band filter, and of course the biggest problem is requiring optical access. So in optical access may not be a problem in a Bunsen burner flame with a glass tube surrounding it, but in a real combustor I mean it is made of metal and putting an optical access and it may be under pressure also 5 bar or 10 bar or 20 bar, so the engineers would not like you to drill a hole and mount something, but then you argue saying that you have nuts there, so you can put a small hole and a bolt and I will mount a fiber optic coupler there, and then I would not mount any transistors there, give me a smallest 1/8 inch hole would be fine or 1/4 inch hole, and then I will use fiber optic cable to take the signal somewhere else and see it, and then you can maybe get one measurement out of it. So we need optical fibers, there is limited field of view and the readings will be quite noisy, and another problem is the flame may shift its location, so you may keep the thing focused somewhere and flame may be one way during one mode, it may go somewhere else during another mode, and so you can have a lot of problems. So it is difficult but you can do it, and there are people working to reduce the cost of these laser based techniques for temperature and so on, like diode based lasers are coming up and so on, but it is not like they are all readily available, that just like you can buy a microphone you can buy a temperature meter with laser and put them, it is not reached the state, maybe 5 years or 10 years later it may be the state. So in summary we have we can use this is the best possible thing, and we can use chemiluminescence with photomultiplier and a combination of fiber optic cables and so on. Is this clear so far? So we have the spice in place, but now we need the forces, so that is the actuator to interfere. So first we have to know what is happening and then you have to interfere. So if I want to know whether you are goofing and I do not see you, then I ask somebody else, is this fellow was studying or has he disappeared or is he into something else, and then once I find what he is into, then I try to catch you and do something to you. So that is the idea here. Now if you speak to an engineer who designs combustors, not a thermoacoustic expert nor a control expert, but just a guy who is worried only about combustion and he wants the combustor to work, let us say someone who designs engines or burners or something, he would say he does not want any active control, even if you are the most lovely active control, it works beautifully, you will still do not want it. He will say that first of all you have to actuate, that means something has to work several times a second, and the combustors typically run several thousand hours, sometimes years continuously without stopping, and they do not think anything else will work so long, but which can move, any movable part can work that long without maintenance. Then he will say that anything you put into it, what are the guarantee that it will work as you desire. See, I may try to find out how you are doing and try to make you study well and all that, but in the process I may make you get upset with everything and you may just completely quit also, that is possible. You put an actuator and then okay, you may had a very bad second mode instability, now that is conquered, I mean that is quelled, but you have a very large amplitude first mode instability which you did not have, and that happens in thermoacoustics very peacefully. So to avoid all these things, and then you have to spend a lot of money extra for this, design the controller, to design a controller you have to pay the controller, the guy who designs quite a bit of money, and then the actuator and sensor and all that, and you have to modify the design, put it in, so all that will cost quite a lot of money. So the engineer will say he will reduce the equivalence ratio or reduce the heat release rate if it comes, and he will deal with it. I do not want to deal with this active control, and people have set up these things in real combustors, we will speak about it, but unfortunately there is not that much confidence that these things will work peacefully, robustly, and like there are other places where dynamic systems can be controlled. For example, in aircraft, I mean it is highly risky system, you are flying and you can fall down, and but you have controls are all electronic, and there is a controller which is often doing it, and the whole thing can work by itself without having a pilot, and that kind of so that is probably much more riskier, but people actually fly unstable aircrafts controlling purely with the controller because they have so much confidence on the theory and its implementation. So in thermoacoustics, to be honest, there is no confidence on the theory at all, and still everything is very much debated, and everything may be wrong, and even if it's right, I mean, see, if you read thermoacoustic book, they will say that, oh, this is the theory, you have n-term model, you have this, you have frequency domain analysis, time domain analysis and all that. You can say that it's like politicians. India is a great country, democracy is thriving, everything is wonderful, we are shining and whatnot, but if all these things were happening, you wouldn't have to say that. I mean, people would be happy on their own. It's like aeroplane, they don't say that. If you speak to aircraft control people, they don't say that we have theory and theory is wonderful and we have wonderful actuators and all that. They don't say anything, they just make these things work, that's all. Whereas because everything works, they don't have to keep saying. Whereas here we say that we have recently understood everything and we are making marvelous progress and blah blah blah. That means there is a lot of problem. So if you speak to engineer, I mean, this is the truth, I am saying very bluntly, they would not be very keen on putting your active control. People are, some companies have one or two episodes done this, but if it was wonderful, it would have caught on. But that doesn't mean it won't come tomorrow. Suddenly something may change and suddenly everybody may use it, and these things cannot be predicted. So at the moment I will speak about what is the status, and for everything, for a long time nothing happened, and suddenly overnight something happened, and then suddenly everything changed. So maybe we are in for an active control revolution in thermoacoustics, and you may be the one who is doing it, you never know. So that's the hope with which people work, and we only work as scientists, we want to have fun, and we don't care about anything. As a combustor guy, he wants the combustor to burn, so you will see if this guy is having fun and he is making something, if it is going to work for me, I will buy it, otherwise leave it. So the economics will take care of itself. So we speak about actuators, which are a major irritant in this active control, because like I said, engineers don't believe that these things can work for so long. So satisfactory actuation of combustion systems present a real challenge, because you have to operate these actuators under high temperature. So the first, if you look at the history of combustion instability control, it's first the active the anti-sound concept came, that is the active control of sound by sending sound out of phase with the incoming acoustic field. So that's like you might have, I don't know, some of you may have the speakers like from Bose, which will cancel the aircraft noise or train noise and so on. So then people try to extend the same idea to thermoacoustic instabilities. So you can control laboratory combustors like Bunsen burner with a duct around it or something peacefully with loudspeakers, and the first actuators were loudspeakers. Loudspeakers do have high frequency response, they have high fidelity systems and so on naturally, but they are not sufficiently robust for using in industrial systems. You mount a speaker on a combustor, tomorrow it may not work, something would have burned or shorted or something, and it needs cooling to work under hot conditions, and the power requirements become prohibitively expensive at larger scales. I mean, the amount of power that is required is, I mean, you have 160 or 170 dB oscillation in a combustor, so something comparable to that magnitude has to be put in, and that's nothing compared to the speaker powers that are there in even big auditorium. So I mean, that kind of power actuator needs in a combustion system cannot be given by loudspeakers. So those are the three main problems. Let me repeat. The power requirements are very prohibitive, and the speakers are not that robust to work in this combustion environment, which is dirty and high temperature, and it needs cooling, which is again makes things very complicated. Cooling may be peaceful in a laboratory combustor, but cooling of loudspeaker in an industrial burner may not be that easy. So then we have to come up with some other means of actuating, and so easiest way is to modulate the fuel supply. So you just fluctuate the fuel supply somehow with a valve which in the fuel supply line which is fluctuating, and then you can fluctuate the fuel supply line, and so you are actually fluctuating the fuel supply line means you are actually fluctuating the heat release rate. So you can fluctuate the primary supply line, or you can inject fuel in a secondary way somewhere else and have heat release rate and use that to have damping, because if heat release rate is out of phase with the pressure, it can damp. So it's like use the devil to fight the devil or something like that, and then absorb the sound which is generated by heat release at some other place by this heat release tries to take it out. So this is possible and it has been practiced, but for ideal actuations a fuel valve should have a linear response to allow linear control theory to work. So if you had some other control theory which does not need the fuel line to be responding in a linear way, then we could be having we could use any valve. But the problem is our theory will work only for, I mean we are using linear control theory which is simple, anything else nonlinear control theory is very complicated. So So large bandwidth was not a problem for loudspeaker, but for valves it may be a problem because you are basically fluctuating the area and therefore it may not be that easy, and not only that, you have to have, if you have to have a sinusoidal, get a sinusoidal response, the area has to fluctuate sinusoidally, and at low frequencies you will get a sinusoidal response, but at high frequencies even if you get the area to fluctuate sinusoidally, which itself is very complicated, you have a valve, you open and the opening and closing has to be sinusoidal, which is not that trivial, although people have made such valves. The other thing is, even if you have sinusoidal variation it may still generate harmonics, so it is not that easy to get this. Then we need sufficiently large control authority that means we have to pulse enough flow rate so that you can get enough acoustic power being absorbed by the secondary heat release rate. So you have to have so this was the big problem with loudspeakers, but here I think it is possible to get sufficient control authority, and we need small amplitude response that does not exhibit hysteresis. And fast response time, because if the small amplitude response should not exhibit hysteresis, and usually it does, that is the problem, and then you need fast response time, because if the response time is very slow, I mean we are talking about inherently fast oscillatory phenomena, so it will not work, and good robustness and durability. So you have to have this work for several years without any problem. So the people who make these actuators, they say that for example in cars you are having this fuel injection cars and they are working for many years without any problem, but for some reason the engineers do not have that much confidence in the system. So we do not have something which has all these qualities, I mean it does not exist, so we kind of have a little bit of this, little bit of that, or quite a bit of this, quite a bit of that, so that we can get it to work. So that is the idea, but these are the desirable quantities. Furthermore, we should take care that the acoustic, the pipe work or the ducts which connect the actuator to the fuel injector position, they should not have large response, because otherwise that system may have either sluggish response and then you may not respond at all, or if it has very good response then it may set up some other instability by itself. So we have to be careful. So obtaining a satisfactory fuel valve is one of the main challenges that faces the reliable implementation of feedback control on practical combustion systems. So this is the main, at least that is what the experts say. In my opinion, the two problems, one is the theory itself is not proper and understanding is not proper, but I think if you speak to experts in the subjects, they are experts and they understand everything, so they would not agree, but this is my personal opinion, is that the theory is all not proper. So that has a lot to do with if you do not understand your system properly you cannot control properly, that is my opinion. But the mainstream opinion is that theory is all well understood, but nevertheless even if it is understood you need very good actuators, and that is which the engineers have full faith on, and that is where the problem is, at least that is what the community thinks. The first fuel modulation systems were on off car fuel injector valves and they are non-linear. So but then people started using solenoid valves which have the advantage of a linear response, and the problems are limited bandwidth and control authority, and you have hysteresis at low amplitudes and not sufficiently durable for practical applications. The car on off valve in automobiles, they are durable and all that and so on, but they are not linear, so that's control theory, people do not like it because we have linear theory. And then there is this magneto-restrictive valve which combines fast response time with increased bandwidth and show promise as long as control authority can be maintained at high frequencies, and it's the control authority comes down at high frequencies, and these are also expensive valves, so that is where things are. So there are different kinds of active control designs, and one is model based control, another one is non-model based control. The non-model based control design considers it treats the system as a black box, and then we have to learn its behavior, so we will look and find out, that is called a system identification procedure. So we will look at so you treat it as a black box, and then we have a system identification to find out about its behavior, and we can identify the system before we keep the controller and find out about it and then start controlling, or we can let a controller be on and simultaneously find out the system as well as control. So one is called offline, so we can have offline or online identification, both kind of system identification exist. So the big advantage of online system identification over offline system identification is that controller keep track of changes in the combustion system dynamics due to varying operating conditions. So for example, the mean temperature may be slowly rising, or maybe the fuel composition may change slowly and so on. So if there are changes in the parameters, then the online identification procedure can identify adaptively and respond to these changes in the operation of the combustor. So non-model based control is attractive because they can be universally applied. So if you are having a model based control, for each thing you control you have to have a model based you have to have a model, and then you have to write models for each system, and then you have to try to control. But if you have non-model based control, then you just treat it as a black box and then get it to work, and so therefore you can use it anywhere. But the biggest drawback is that there is no guarantee that the controller will work. whereas if you had a model based controller we could actually theoretically give some guarantees, at least on theory it works. So in practice if it does not work there must be some problem with implementation, whereas this you set up a controller but there is no mathematical guarantee that it will work. A model based control design requires a detailed knowledge, that is a model of the unstable system with the actuator and the sensor, and based on this model based on this knowledge the model based control design can provide strong mathematical guarantees that it will not go unstable and cause harm. So since the combustion system is known to the controller you do not need to have any system identification required. So of course the model based control can be either be designed for fixed operating point or it can be designed for a varying operating points. So the dilemma while designing an active controller is, so either the controller does not need to know about the system but there is no guarantee that it will work, or the controller can give guarantees but you need a detailed knowledge of the system, which would mean equations and solutions and all that, which is difficult for practical large scale combustors. So this is the challenge there, as to go this way or that way, and that has to be based this challenge has to be tackled based on the specific system that you have in your hand.
Why shouldn't we start with a model-based system and like change the parameters based on the system size?
Yeah, there is no problem with that as long as you have a model. If you do not have a model then you can't start with a model based.
You can start with a basic model, a simpler model instead of
For some systems like a dumb combustor which you saw last time, or a swirl burner, I think even the basic model may be quite involved. So if you have a model, yeah, then you can do that, and then you can couple it with non-model based identification and you can have a hybrid thing and so on. A lot of things can be done, but it may not be there. If it is there, yeah, I can do model based control, and then there is a guarantee that it will work. Yeah, it's a good point actually, but it's a difficult question what you are asking. Anything else? We'll stop here and we'll